Back when I was in college, on the very first day of my statistics class, my professor asked a simple question. In this room of 30 people, do you think two of us share the same birthday? We all looked around and thought, probably not. I mean, there are 365 days in a year, and only 30 of us. The odds seemed pretty low. But the professor was willing to bet that two people would share a birthday. Did he know something we didn't? Ha! Of course he did. One by one, we started saying our birthdays. March 22nd, January 15th, October 8th, and then only a few people in May 20th. And someone from the back just shouted out, "That's my birthday too." So what's going on here? Why is it so likely to find a shared birthday in a small group?
When we think about the chance that any two people in the room share a birthday, that includes you and me, you and that person over there, me and that person over there, all the possible pairs, which in this case is 435 pairs. This is why the probability of a shared birthday is so high. So in a room of just 23 people, there's a 50% chance that two people share a birthday. And in our class of 30, the probability skyrockets to over 70%. Let me show you. The calculation is based on finding the probability that no two people share a birthday, and then subtracting that result from 1. It is done this way since the alternative is much harder because a shared birthday could happen in so many ways. Two people could share a birthday, three people could share a birthday, two separate pairs could share birthdays, and so on. To make the math easier, we'll leave out leap years and just use 365 days. For the first person, there are 365 possible birthdays. Since they're the only one, their birthday is guaranteed to be unique. So the probability is 365 out of 365. The second person must have a birthday on one of the remaining 364 days. The probability of this is 364 out of 365. For the third person, there are 363 days that don't overlap with the first two. This pattern continues for each person in the group, and to find the total probability that all birthdays are unique, you multiply these individual probabilities together. So, when we reach a group of 57 people, the probability that all of them have different birthdays becomes really small, merely 1%. That means that the probability that at least two of them share a birthday, which is the other side of the coin, is over 99%. If this scenario were the other way around, it would be pretty hard to be in a group where no birthday is repeated. This made me think, how large must a group be to ensure that every single day of the year is represented by at least one birthday? In this case, the probability builds much more slowly because it becomes increasingly difficult to find that last missing birthday. You'd need around 2,200 people to have a 50% chance of collecting all 365 birthdays. And to be 100% certain, the group could just keep growing, since there's always a tiny non-zero chance that one day will be missed. As the group grows, an interesting observation is that some birthdays will have appeared many times, while others will appear nearing the end of the group. If you reach 4,000, while you're still waiting for that one final date to appear, the birthdays have repeated on average around 11 times. This could mean that one date appears one time, and at the same time, another repeats 21 times. Over the years, I've kept my eyes open to finding someone with my same birthday. I'm still yet to find someone. However, I don't really know the birthdays of everyone I know, so maybe there's someone there. But the probability of this is even more remote since I'm asking for a specific date to be repeated. In this case, knowing 100 people would only give me around 24% chance to know someone with my same birthday. And for a 50% chance, I would need a group of 253 people. Now, remember that having a small chance, like 24%, in a group of 100? Some people will fall in this group since I know people who do know one or even two people who share their same birthday. This also got me thinking. What are the chances of someone being born on the same day of a parent? At first, I thought that would be minimal. But then I remembered, I know at least two people who share a birthday with a parent. So the odds can't be that far off. In this case, approximately 0.55%, which is 1 in 182. Now, this probability calculation is only valid when the event is random. If the parents timed the date, the odds would skyrocket. However, most of the families I know have more than one kid. So if we consider a family with 3 kids, the odds increase to approximately 1.63%. This probability is an average for a single family. It means that for any one family you look at, the odds are low. However, when you observe a large number of families, the likelihood of seeing a low probability event happen at least once or even twice goes up significantly. What feels like an incredible coincidence often isn't. Our brains are very good at finding patterns and noticing rare events, but they're not very good at accounting for the sheer number of opportunities for those events to occur. You know a lot of families, and over that large sample size, seemingly improbable things become quite probable.